How's it going there, Eunice?
Very well, thank you.
Way to go. Good. So I'm just going to invite your colleague, Paul. Paul, I said getting my P's mixed there. So he's just accepted. He'll be online right now. How's it going, Paul? Eunice, it's good to see you both. Way to go. So look, yeah, really just want to say thank you from the bottom of my heart for presenting at these events. It's a lot of time, a lot of effort. It's all free, so we do it for the community. So it wouldn't be anything without our lovely presenters. So yeah, folks, ready when you are. If you want to kind of jump into your presentation, we've got some hungry robot professionals keen to hear what's going on at Avidbots.
Great, wonderful. Thank you. Thank you for the invitation, Adam. It's a pleasure for us to be here tonight. And good evening, everyone. My name is Eunice Poon. I'm the Director of Robot Autonomy at Avidbots. I'm here tonight with Paul, our sensor software developer, to present about 3D sensing in autonomous commercial cleaning. So first, a little bit about Avidbot as a company. So Avidbots was founded around 8 years ago by 2 University of Waterloo graduates. And really, it all started because we noticed that there was a constant need for automating cleaning in large commercial spaces. And this trend will likely continue with more than 3 million cleaners needed in the US alone over the next 10 years. And because the task itself is highly repetitive, we're seeing high 300% manual job turnover for this role. And this is where NEO comes in. It is what motivated us to develop NEO, our robots, to address the labor shortage issue. So for those of you who haven't met NEO yet, here is a video showing where NEO is being used today. So NEO has been deployed in many leading airports, warehouses, malls, manufacturing sites around the world. And we feel that there are a couple of features that set NEO apart from its competitors. First, NEO is a fully autonomous robot. So there are different levels of autonomous vehicles, and NEO is a level 5. What that means is that it is capable of navigating fully autonomously without having to require manual assistance or intervention. It is also intelligent enough to respond to obstacles and changes in the environment. And with its 14 sensors, it is able and capable to operate safely around people and other autonomous devices. And lastly, all of our robots can be seen in action in real time. And our remote monitoring team is always on standby to assist and just to make sure that in case the robot runs into any situations, it is able to navigate safely and without requiring human assistance and babysitting. And if we were to go beyond autonomous cleaning, we are seeing a lot of opportunities in this space with NEO. Our vision is that NEO is really an autonomous platform. So just like a human, instead of having a robot that performs a single function, we're seeing that NEO is capable of performing multiple functions. And today, NEO is already capable of performing cleaning and disinfection together. And we're excited to introduce further applications, be it monitoring or security, to our robots in our future generations. So going a little bit deeper into the technical side, if we treat autonomous commercial cleaning as a problem, there are really a number of technical hurdles we need to overcome. So when our customer first receives the robots, they will work with our team to create a map of the environment and a cleaning plan. From that point on, our robot is capable of navigating autonomously. So in order to do that well, there are a number of core autonomy capabilities that we need to realize. First is 360-degree obstacle avoidance. So our robot has 360-degree visibility, and it doesn't have any blind spot. What that allows the robot to do is to react and respond to obstacles that are coming at it from different directions, like the one demonstrated in this video here. Now, detecting obstacle in the environment is not new, but what makes it challenging is that we need to do that fast enough without slowing down the robot. And the second capability we need to realize is advanced dynamic planning. And because we are in a cleaning application, what requires us to do is to be able to dynamically replan without compromising on our productivity and area coverage. As is demonstrated here in the second video, a lot of times we need to navigate in very tight environments while still being able to clean the maximum floor space. And lastly, the third capability is lifelong situation awareness. And what we mean by that is that while a lot of other robots may require assistance in remapping and retraining from time to time, NEO is capable of surveying the environment before it starts so that it can react dynamically. And what that allows us to do is for NEO to operate without having someone constantly going back to it and babysitting it. So that defeats the purpose. Now here is an example illustrating our approach to fully autonomous planning. So when we think about autonomous planning, there could be different approaches. So one approach is to just keep going until you hit something in a blind manner. And the second approach is what we call here on the left, semi-autonomous planning. So some of the other models might choose to use a teach and repeat approach. And what that means is that someone will teach the robots its path, but the downside of that is any unexpected events will result in the robot stopping and requiring someone to come to its attention. In contrast to that, NEO's approach is fully autonomous planning. What it is capable of doing is instead of assuming a fixed path, it actually surveys the environment, and it is doing that every time so that it has the capability to react elegantly, whether you have people walking around or unexpected vehicles driving by, it's able to do that and then come up with the optimal path. So I think that's all I have for autonomy and capability. So I'll pass the time now to Paul to talk about 3D sensing.
Thanks, Eunice. So my name is Paul Belanger, and I'm a software developer on the sensors team here at Avidbots. Now, in a fully autonomous robot, we need good sensing in the environment, and that includes sensing of the 3D space around the environment. Now, at Avidbots, we have a variety of constraints that can make 3D sensing particularly difficult. First of this is operating in an uncontrolled environment. So NEO can operate basically almost anywhere, from the dirtiest warehouse to the cleanest fine retail and basically everything in between. In most of our sites, we don't have the luxury of modifying the environment. So things like installing fiducials, lines on floors, and all of that, it just isn't feasible at most of our sites. The site itself can also change on a daily basis. Think, for example, warehouses that turn over their inventory daily, or retail sites with changing seasonal displays and even day-to-day stock level changes. So basically, our 3D sensing system must be able to handle a wide variety of environments and be ready to adapt to change. Second, lighting conditions are also ever-changing. So some sites, we're bathed in direct sunlight directly overhead. Think transport malls, big shopping centers with huge glass ceilings, things like that. In other situations, we have fully artificial light, things like windowless warehouses or long corridors and education centers, things like that. Some sites even have both environments at the same time, so coming from a long unlit hallway directly into full sunlight. And so our 3D sensor system also has to be adaptable to a wide variety of lighting conditions. We can't just set it and forget it. Third, unknown obstacles. So NEO operates in the public, and basically this means that anything can happen at any time. Many sites are a literal zoo of different obstacle types. You have people walking around, pallets, signs, cliffs, wires hanging everywhere. There's a lot of different things that NEO can run into when it's doing its daily duties. And one thing we found in running NEO in lots of different locations is that you will always find some situation that hits on every corner case you could have thought of. And then you'll also find situations that hit on the corner cases that you could never have even imagined. And that makes it difficult to plan for some contingencies. And just to add to that, these obstacles can approach in any direction. So our 3D sensor system must be omnidirectional and adaptable to deal with this wide range of obstacles that we can encounter. And finally, low latency. So again, NEO operates in the public, and what this means is that our standard of safety is very high. Minimum stopping distances means that obstacle detection latency affects our max speed, and ultimately our max speed affects our cleaning performance. So for example, each 10 milliseconds of processing delay on our obstacle detection adds an additional 1.3 centimeters in total stopping distance. So keeping the 3D sensing system as quick as possible is essential to maintaining maximum speed. So now that we understand kind of some of the challenges that our 3D sensor system has, what are some of the sensors that we can use to achieve our goals of sensing the 3D environment? So I've pulled together 4 examples here. So first, let's talk about LiDAR. So LiDAR, it works on a pretty simple principle. So you have a pulse of light that is emitted by the sensor. That pulse of light travels through the air, hits some surface, reflects off that surface, comes back to the sensor, and then what the sensor does is it measures the time between when the pulse was sent and when it is received, and turns that directly into a distance measure. Now, these LiDAR sensors work over a wide range of different distances. They're generally highly accurate. Now, your basic LiDAR unit will measure depth only in one dimension, so think like handheld rangefinders, things like that. However, by putting these basic LiDAR units around an encoding axis, you can then measure an entire plane of 2D points. And by having additional orientations of the lasers and different geometries, you can get up to full 3D area scanning with LiDAR. Now, another evolution of LiDAR is what we call flash LiDAR, which is instead of illuminating a single point with a laser and then measuring the return, instead we emit a flash that covers the entire scene all at once. And then instead of using a single laser receiver to receive that pulse back, we use an image sensor to receive light from the entire scene all at once. So this gives much denser information than regular LiDAR, gives more coherent information because you can expose the entire scene at once. However, because the light isn't focused on a single point, maintaining the same power ratings and eye safety for your emitter and everything, the light just isn't as intense, which means that your accuracy and your maximum range are both reduced somewhat significantly. In addition, there are also some materials that are simply invisible to the flash LiDARs. Third up, we have stereo 3D. Now, stereo 3D takes a completely different approach to depth sensing. So instead of using a laser, it uses 2 cameras with a fixed baseline between them to derive depth. Now, the stereo 3D, it uses an algorithm based on parallax, which is very similar to how human binocular vision works. At a high level, the algorithm is pretty straightforward. First, find corresponding features between the left and the right images, and then find the difference between those features, which gives you your disparity. And then that disparity is then transformed into a range, where if you have a very small motion between the 2 cameras, that's a long range. And if you have a very large motion, then that is something very close to the camera. Now, there are 2 types of stereo sensor, what we call passive and active. Now, a passive sensor is just that. It simply listens and views the scene in its natural light. And so is very susceptible to lighting conditions. And then there's also active 3D stereo, which augments the 3D stereo system with an infrared pattern projector that projects a pattern of grids or dots onto the scene, which can be used to fill in correspondences in areas that might have low amounts of features otherwise. Usually this pattern projector is in infrared just so that it's hidden from human vision. And so you don't see dots being projected everywhere, just walking around the sensor. And so therefore most 3D sensors are stereo sensors are work in both visible and IR light. And finally, I'll mention ultrasonic sensors. They're similar in theory to LiDAR, but they use sound instead of light. So they emit a pulse of sound, listen for the return, just like a bat. Now, generally, these are one-dimensional sensors, generally a lot lower resolution and range than LiDAR. And when you start stacking them together, interference issues start to crop up a lot sooner with ultrasonic, just due to the nature of sound. Now for NEO, we primarily use both 2D LiDAR as well as stereo 3D for our perception. And next, I'd like to talk about just some of the challenges that we faced, especially with 3D stereo that we've found in a lot of our sites. So if you remember that the first step of stereo 3D is to find correspondence between the left and the right images. Well, there are a number of ways that this part of the system can be tricked. For our first example, we have glossy surfaces. Now, a shiny surface will reflect sunlight and other overhead lights, just like a mirror. So you can see in the first image here that that we have a series of LED lights under the shelves in this retail area that are reflecting off the floor and being seen almost in a mirror image. And just like optical illusions for humans, it's difficult for the correspondence algorithms in the stereo sensors to discern this mirror image from where the true floor is, which leads to inaccurate depth data. In fact, NEO is even kind of self-defeating in this way, since our goal is to scrub the floors as clean as possible, and generally a clean floor will be a shiny floor. Next up, we have low reflectivity. So with active 3D stereo, being able to see the projected pattern is essential to getting good data from the sensor. So what happens when the surface you're projecting onto doesn't reflect IR light at all? Well, in situations like that, you have basically a hole in the image. So in the image here, this is one situation we found where there was a barbecue painted with black paint that was completely invisible to the sensor. And so our system then had to be robust enough to deal with this sort of hole in the data and route around it intuitively. Finally, just like the human eye, camera sensors have trouble seeing both very bright and very dark things at once, which generally leads to saturation in images in areas where you have reflecting overhead lights or sunlight, things like that. And so you end up with a washed out image like this third image here. And in these washed out areas, there's no data available basically for the correspondence algorithm to find what pixels in the left image and the right image correspond to each other. And this can lead to things like missing data, like in the barbecue case, but can also lead to more sinister things like spikes coming up from the floor, great pits in the ground. Now there are some ways to combat this. HDR imagery is one. It's helping a lot, but this is still an ongoing issue with stereo cameras. And finally, the last one I'd like to mention is repetitive patterns. Now, these introduce uncertainty when identifying corresponding features, because if you would imagine vertical slats, for example, does this vertical slat correspond with this vertical slat or this vertical slat in the corresponding image? That uncertainty can lead to incorrect depth data being generated. And the sinister thing about it is that repetitive patterns are everywhere in a lot of environments. So things like checkered or tiled floors, slats on shipping pallets, piles of folded linens on a shelf, anything like that has a potential to cause problem for stereo sensors. So given all those challenges, what can we achieve with NEO today? Well, we're able to clean autonomously at over 1.3 meters per second. We're able to detect all the obstacles within 3 meters of NEO and stop or reroute as needed. We're able to detect all potential cliffs in our navigation path, and we're able to automatically detour around these obstacles most of the time without even stopping. And so we're able to keep quite a high productivity in the robot. But what are we looking at in the future for kind of where NEO's going with its perception pipeline and what we're doing? Well, first is semantic understanding. So this means when you see an obstacle, not just seeing that there is an obstacle, but understanding what that obstacle is and then reacting accordingly. So things like as robots work in busier spaces, we'll have to be really smart about how we navigate the world. So for example, humans are generally predictable. They can move at any time. And so giving humans a wider berth could be one application of this. As another, vehicles such as forklifts, intelligent avoidance so that we steer behind the forklift, not in front of it, or things like that to increase productivity are going to be big moving forward. And now second, integrating next generation AI into the NEO platform is also another thing we're looking at for the future. So by leveraging AI, we can reduce our reliance on purpose-built sensors, move towards commodity hardware such as off-the-shelf cameras instead of bespoke stereo sensor assemblies. We also want to be able to learn from our past. So NEO has cleaned thousands of hours across hundreds of different sites. And by incorporating that knowledge into the system, we hope to make smarter decisions in the future. And this will help us achieve our goal one day of bringing robotics to everybody. So we're always looking for people who are passionate about robotics, and there are dozens of open positions available across Avidbots in all departments as we speak. So if you're interested, come help us change the world with robotics at avidbots.com/careers. Thank you.
Awesome. Way to go, Eunice and Paul. Thank you so much for the content. There's lots of really, really great information there. The infographics, I think the work you guys are doing is super cool. And it's a Canadian robotics company, folks. So definitely all aboard for that. Cool. So want to jump to one of the questions, and this is certainly the time if anybody did have questions in the audience, please plug them in the Ask a Question tab. One of the questions we have, for the processing, what kind of compute hardware does NEO use? Also, for deep learning algorithms, do you use NVIDIA Jetson or any other kind of GPU?
So yeah, the hardware in NEO is very similar to what you would find on a normal desktop PC. So we use a lot of industry standard libraries and systems for our pipelines. A lot of the inference itself is done on an ASIC hardware, so it's done. We do offboard processing. At this time, we don't utilize any NVIDIA compute capability. It's mostly living in the Intel ecosystem right now.
So somebody has asked, do you use sensor fusion between lidars and cameras?
Yes, we do combine information between both lidar and camera to make our obstacle avoidance and navigation decisions.
Yeah, very good. Alrighty, thanks for that, Mohammed, for your question. And yeah, as Eunice and Paul mentioned, Avidbots are certainly hiring, so you can check out their website for any roles if you're interested. And yeah, just want to say thank you both so much for presenting tonight. Really, really, really grateful. Sorry, Zebra wasn't here, but like I said, the show must go on. So yeah, it was a short and sweet one tonight. So Eunice and Paul, we've got another question. Let's do it. I like it. Salim has asked, how far are you from using Avidbots for security? Ooh, product diversification. What are our thoughts there? We're going to strap security cameras and laser guns.
It's definitely on our radar. I guess I'll let Eunice take this one.
So like I mentioned, that we do see NEO as a platform. So there are many different applications we're considering. So security is one of the possibilities, and definitely I think is something that we're considering.
Yeah, there's a company in Canada that already, I can't remember the name off the top of my head, but they specifically do kind of this security surveillance kind of robot stuff. So yeah, look, I'm super excited to see. I know there's a lot of iterations of the product coming out, smaller Neos with the disinfectant spray, the floor scrubber. So it's all on the up and up. Really excited for the future of Canadian robotics, and similarly Avidbots kind of leading the way there. So Eunice and Paul, thank you again so much for stepping up tonight. Really, really grateful. And yeah, I guess that'll be it from us tonight.